Thank you. So, morning, everybody. Everyone, all 7 of you in this room, 8, and hopefully the other 200 were on the other side of the camera. So, this last lecture of the course, this is the last lecture, and it's my pleasure and honor to introduce my old friend and previously a student and TA at IDEO, Alex Lutzenberger. Alex is CMU grad. And after leaving CMU, he actually founded a startup which now has a large number of employees down in Wilkinsburg and a couple of other places around the world. And his startup is all about applying computer vision technologies of not a very particularly complex kind. And basically, the level of sophistication that you have already learned if you've done all of your homeworks during this course. He's going to, over the next hour or so, he's going to talk about how you can take what you learn and take it out into the real world, make a real product with the right imagination, the right design, and actually make an impact. So let me turn this over to Alex. It's all yours.
Thank you. So
everybody shut your laptops, all the usual rules, right?
As Bikshra was saying, talking about my company, Agot, and kind of making a bit of a comparison with the things that you'll have learned in this class and how we kind of apply it all at Agot. And, in a startup in the real world, not necessarily generalizing to all those cases, but at least our experience there. So I'll start out with a bit about Agot. And so we are kind of a computer vision company, but more broadly, the vision of it is humans are imperfect and can only see a portion of what's happening. If you are using cameras and AI, you can see everything that's happening in a restaurant and use that information to maximum effect. And so, this can be used in a number of ways. A few of kind of our current products are advanced analytics, streamlined drive-through, and real-time order accuracy. So real-time order accuracy, I'm sure if any of you have ordered fast food, you have sometime or another gotten a case where you didn't get exactly what you ordered. And basically what we do there is we watch the preparation process with cameras, and we intervene to prevent those incorrect orders from going out the door and make sure they're corrected, get delivered to the customers correctly. And then some of the advanced analytics, looking at how people are actually working in the restaurant, how ops procedures are being followed, what ops procedures are effective and lead to kind of higher throughput, accuracy, labor utilization, all of these things. And then the drive-through as well, using the information about where cars are and the state of the kitchen to make informed decisions about things like if a car should be routed to a waiting bay, if somebody should be prepping on the drive-through line rather than the in-store line, and really trying to make use of this data, not just to analyze and find out what happened, but to make better business decisions in the moment. And so kind of some sample video of order accuracy and what that looks like, just to give you all a bit of an idea.
Replacing gadget is quickly becoming the most popular Christmas gift of 2020.
Okay.
That is.
The volume's too high.
That is also not the correct link somehow or another.
No, I think it always, because you're on YouTube, it gives you an ad before you do anything.
Oh, okay.
So all of you guys are going to get a free ad along with.
There we go. Second time's the charm.
Agot.AI provides interventional order accuracy technology that helps your team consistently delight customers with accurate preparation of their orders, no matter how customized. Agot observes the entire order preparation, tracking each ingredient that is added to a meal item. When the employee finishes preparing the order, the Agot system checks that order against what was communicated on the kitchen display system to confirm that each meal item was prepared correctly. If an error is detected, the Agot system alerts the employee through a message on the kitchen display system, allowing them to correct the error before the order is delivered to the customer. In this case, the employee forgot to add pickled onions to the rice bowl, but Agot's error notification allowed him to correct the issue. Agot's platform captures previously inaccessible data and provides unique analytical insights to help drive operational improvements in the restaurant. Visit Agot.AI today to learn more.
So basically just to give you a little taste of kind of what that looks like, we are having cameras overhead watching the preparation process, and kind of importantly, what is actually prepared is a function of the entire preparation process. So this isn't a case where you can just look at the meal at the end of preparation and determine if it's correct or not. It's really a function of that it was the same bowl that had rice in it that was supposed to have pickles in it that did not. That was kind of a demonstration video from a partner restaurant, but a lot of the restaurants that we are working with have, I would say, significantly more difficult operations where you have a lot of small items, things moving quite quickly, and I'll kind of get into that a bit more. And so, particularly with the order accuracy project, there's lots of occlusion. So not only with people's arms, other objects, there's also kind of kitchen elements. A lot of these kitchens, for maximum efficiency, are very vertically stacked, and that means that a lot of the prep actually happens kind of under equipment where you can't effectively see. And you can imagine if you have several burgers and they all have the buns on them, you can't do too much with their appearance because they look very, very similar. And also more broadly, we need to compose a lot of kind of low-level vision information towards some higher-level objectives. And there's a very high level of accuracy that is required to do this effectively, since most of the time the employees are preparing the meals correctly. And so in order for most of our notifications to be correct, we need to be having as high or similarly high level of accuracy in terms of our accounting of what was prepared to allow that level of accuracy as far as the interventions. Basically, just because the base rate of errors is higher than anyone would like it to be across the fast food industry. Typically, about 15% of orders have some sort of mistake. But if you look on the level of the item and the ingredient, then that corresponds to needing to have a very high accuracy to produce the interventions well, to not slow down their operations, but still allow them to correct the errors. Objects can move relatively fast and erratically over large views. Again, this was a relatively kind of calm video there, but a lot of fast food preparation, people are moving as quickly as they can, and kind of over the course of a few minutes preparing a large number of food items. And as I was mentioning, it can be surrounded by functionally identical other objects as well. And on top of that, there's a lot of data. So you can't just treat this as a function of the end state of preparation. You really need to understand the preparation process and know that that it was the same meal that had one item, had one ingredient, and also had another. So if somebody ordered a burger with pickles and no tomato, it's important for us to distinguish that from some other burger that was not supposed to have a pickle and was supposed to have a tomato. And by the time they add the tomato, that pickle may have been long ago concluded, and so we need to keep track that it's the same object over kind of significant periods of time, and significant occlusions, multiple cameras, all of these things. And so we operate on like 1080 by 1920 frames. There's 3 color channels. There's 2 to 15 cameras that meals are kind of prepared over. And meal preparation takes about 3 minutes. So in terms of the raw data, for instance, it's like 56 to 419 gigabytes, and the actual order that we are trying to predict to make sure it's correct is about 10 bytes. So it's a lot of data for the end signal. You don't have to store that amount of raw data because video codecs are fortunately very efficient, but there's also hundreds of instances of orders per day, per store, and thousands of stores per brand. So you've really got a lot going on and a lot of data to process to ensure that this is effective. And just compared to some other notable data sets, it is a lot of data relative to kind of the end signal that's predicted. And as you kind of have all learned in this class, inductive biases are kind of helpful for dealing with a large amount of data per signal, because you are imposing some structure on the solutions to the problems. You can do image recognition with an MLP, but you're much better off doing it with a CNN and imposing that structure on it, because you know there ought to be things like positional invariance. And so kind of having even more data accentuates the need to do these sorts of things. All of those are kind of rough estimates. So as I was mentioning, we need to be very intentional about how we do it. We need to be efficient as far as compute, and we need to build some inductive biases as far as the structure of the problem. And on the representation and the labeling front, this is kind of a very, very large amount of data to just get fully labeled. So it merits some thoughts in terms of the way the problem is represented and what is actually labeled to be efficient, and to also get a breadth of instances. There are a lot of customizations that can be done to the meal items, and you want to make sure you're seeing at least some of those, seeing all the ingredients. And if you're getting things kind of very densely labeled, then that's going to be kind of a very expensive proposition. And so, one of the considerations about what's different in a class like 11785 and working on this stuff at a startup is you are spending a significantly larger amount of time asking these sorts of questions of, how do I actually wrangle the data? How do I want to represent these things so that I can make the most efficient use of my resources, be that compute or labeling time or bandwidth, to get the most bang for your buck, so to say. Oh.
That's okay. Yes,
And so I thought I might just kind of list some of the techniques we use and kind of talk about the overlap with this class. And so we use MLPs, of course, CNNs, RNNs, transformers, autoencoders, no GANs, data augmentation. So just about the whole kitchen sink of the things that you've learned here. And they're kind of pieces of the overall system. And each of these has their own kind of accompanying appropriate representations and inductive biases that, as I mentioned, are kind of very important in terms of structuring the problem in a way that is learnable and workable in terms of the amount of kind of labeling and compute, et cetera, that's needed. And so kind of some of the principal ways that deep learning in practice and in industry or in a startup varies from classes in academia. There aren't any public data sets. So we get this raw data from the point of sales and from the cameras, and it's really at that point up to us to decide how we actually want to represent the problem, how we want to pose the problem, how we want to train our models, how we want to get our data labeled, and we effectively have carte blanche with that there are not really, for our tasks, relevant public data sets. So the ball is really in our court for how to best do that. And obviously kind of what exists informs that as far as the network architectures and representations that have been shown to be effective. But it's a much more kind of two-stage process. And let me just skip ahead, actually. Yeah, so in academia, if you're working on a project like in this class or in your research, you might kind of typically find models that work on your data set and build on them, whereas in a startup, kind of the process can resemble something much more like this, where you look for vaguely similar problems, representations that sort of get at what you want to. You figure out how they map onto your problems, and then you make modifications and build from there. And that's just to say it's not necessarily available to you to have off-the-shelf data sets and models that are really getting at what you want to get at. And yeah, as I was mentioning before, there's these trade-offs in terms of the closeness of the representation to the raw data and the tightness of supervision versus the kind of time and effort to get that labeled. And of course, if you have a lower level representation, then you're also putting more onus on getting that translated up into these higher level objectives. So there's kind of a trade-off there, and there's also kind of very practical concerns, like, is this actually matching what my data looks like in practice if you have kind of different a different processing pipeline for the compute running on the edge versus in your training. Sorry, I've sort of skipped around here a bit. And so, yeah, not all data kind of neatly fits kind of well-studied molds, and so sometimes it has a unique structure. And as far as kind of dealing with particularly a problem that has a very large amount of raw data to the amount of kind of end signal that we want to predict, it's important to represent that structure well, because if you don't, you end up just kind of overfitting and not appropriately generalizing, or just failing to fit, or using exorbitant amounts of compute. And so kind of principally, it's kind of different notions of locality and the relationship that it has with other data. And that matters a lot for how you learn. Like I was saying before, you can train a MLP on ImageNet, and maybe you could get it to fit your data, but you probably aren't going to see the amount of generalization that you like. You probably aren't going to have the efficiency that you like, and you're going to have a model that's kind of more broadly just over-parameterized, a lot larger, and on top of that, not appropriately kind of capturing the crux of the problem. And yeah, so not all problems are kind of very well studied, and I, for one, was kind of surprised in our journey so far as a startup, the degree to which there are problems that really come up that are not well studied, that there isn't really material on as far as the literature or effective architectures for kind of off the shelf. And so that sort of leads back into that the process is pretty different. And it, for us at least, has involved a lot of kind of composing different pieces of research and bringing that all together. Do you have a question? Oh, yes. And I would kind of more broadly characterize this as like figuring out what questions you should be asking, but before actually asking the questions and just kind of trotting ahead, you know, is this the right representation? Is this the right way to go about it? Is this the right way to label the data? Is this the right data to label? Is this the right data for us to get? That there's a very large degree of control when you are the one that is installing the cameras, placing the cameras, deciding which kind of product problems are being tackled, deciding how the data is processed and labeled, and the model represents the problem, and how the training process is run. There are kind of a lot more degrees of freedom than there typically are when you are working off a fixed data set with a fixed set of kind of inputs and outputs. Yeah, as I mentioned before, I've been kind of very surprised on this journey relative to kind of my expectations going into it. The extent to which despite the kind of thousands and thousands of papers being published on deep learning, there are kind of significant greenfield areas and blind spots that kind of retroactively seem like pretty significant. So in academia, typically, you know, it varies on the particulars, but you'll be working with a well-defined task, inputs and outputs, and in a startup, you're optimizing kind of a money stage pipeline. have to worry about things like how does your training sampling vary from what you have in practice. This is actually something that happened that at one point the training pipeline ran through JPEG, and you had some JPEG compression artifacts in the training pipeline that were not present in the inference pipeline, and you sort of need to make sure these things are consistent. So very practical problems there. And so, as I was saying, there's a lot of overlap with what you're learning, both in terms of the subject matter, but I think also in terms of the approach. Kind of break down problems, simplify, test on small cases, and make sure you can kind of fit on that before worrying about generalizing, create some toy problems and do them. And kind of for the second part of this talk, I actually wanted to go over some toy problems that are a bit analogous to some of the problems that we're doing, and in some cases kind of help me work out some of the problems that we were facing. But I think actually maybe I'll stop a bit for questions if there are any right now.
You guys have any questions? So firstly, when you started working on this, so the video that you showed, obviously to create all those detectors, you needed to train data on that, training data for that specific domain. How did you start collecting that data? How did you annotate it? How much time did it take for you to get ramped up to just be able to come up with a basic system?
Yeah, so we started out kind of in some restaurants where the problem is sort of simpler than in a lot of the large fast food chains. Unfortunately, we are not able to kind of publicly share videos from kind of some of our larger corporate sponsors, but the kind of problem is significantly harder there than it is in either that video or where we started out, which is actually a local restaurant here on Craig Street, Sushi Fuku. It being a simpler problem made it much easier to get a relatively small amount of data labeled, and we spent time either labeling it ourselves or hiring some folks to label that data to get things started there. And basically, we built a proof of concept there, then presented that to some of the larger brands and started working with them.
So how much data are we speaking of? What is the labeling process now?
Right now, we work with kind of a third-party labeling vendor. I think for our initial kind of models, it was probably on the order of like a few thousand, like single-digit thousands of images that were kind of labeled, but thankfully, due to it being like a relatively kind of simpler problem in that restaurant, that was kind of sufficient.
But still, the number of classes you have to distinguish is not insignificant. I'm sure it's in the double digits, and the variation. I mean, when you're looking at guacamole, there's so many different presentations of guacamole.
Yeah. So I think in Sushi Fuku, it was about 30 classes. With our customers now, it's kind of more on the order of like 80 or 90. And that's actually something I forgot to mention in the earlier slide there. Is another challenge is a lot of the ingredients on the items are very small. So you can't necessarily kind of very easily see it, and it also looks very different if you have like guacamole in a taco versus a burrito. So you kind of effectively end up with a lot of sort of variations of the same ingredient, and that's definitely kind of a a big challenge. And so kind of part of dealing with that effectively for us is integrating the information over time. So not just trying to in one shot get all the information, but using different signals for when an ingredient was added and when an ingredient might be visible to determine the composition of the order.
Also, given the nature of the ingredients, I get the feeling that you're classifying waste more on texture than on shape, right? So you have a two-stage problem here. One is segmentation, the other is classification. Now, segmentation, I understand, is reasonably well defined when you have objects with shape, whereas when you have objects which are blobs and are basically textures, then the notion of segmentation itself kind of gets more challenging to define, right?
Yeah.
So how did you solve these two problems? Because textures are harder to classify, and when you have such a variety of them, and then segmentation is a challenge.
So I'd say as far as it being the texture versus kind of the color, then that actually varies pretty significantly based on the ingredient and the brand. So there are some things that are basically like sauces and they have functionally the same texture, but just different kind of colors. And yeah, you mentioned that you have kind of multiple ingredients there. It's not necessarily a clear segmentation boundary. You might even imagine kind of sauces that they can get mixed up and kind of not even have any well-defined kind of boundaries visually between them. And so that's kind of certainly a challenge, and I think what you're saying kind of hits on what I was describing before, that it really matters picking the right representation to actually make the problem effectively both learnable, but also labelable. And some of the challenges that we kind of face with that are to do with the fact that there are multiple ingredients on an item. Some of them may or may not be included at a given time. It's hard to define a kind of solid line boundary between when an ingredient is visible or not. And it's hard to define good like segmentation boundaries for a lot of these ingredients, that sort of thing.
So again, when you define your classes, now you have a labeling problem. You have to decide on the label set.
Yeah.
What is the process? Because I believe I don't think I think you're not just labeling the basic palette of ingredients that you're given, but you have to come up with your own labeling set, which is some function of these things. So what is the set of labels? How do you come up with the labels? And how do you instruct your labelers?
Yeah. So I think there are a lot of considerations with labeling, and so I could probably give a whole talk just on that. But kind of some of the major ones are, for one thing, while the interventions are on the level of like what in the menu did they get wrong, a lot of places will allow you to order the exact same thing in multiple ways. So you could either get like a cheeseburger or you could get a burger with cheese, and there is no logical way to visually distinguish those. They're preparing the same thing, and so you, for one, need to make sure that what you're actually representing them as is something that like exists in the data that you're looking at. That the distinction between a cheeseburger and a burger with cheese exists in the point of sales data, where they are representing that and displaying that to the employees, but it simply does not exist in the real world. So there's kind of no functional way to establish that. And then you get into the particulars of the representation that's being used for labeling, and also the loss function, because it's not just the representation that matters there. That effectively the loss function dictates the semantics of your network outputs. So, you know, the only difference between kind of several sigmoid outputs that you have is the label for those binary outputs that you're actually using. And if you are kind of likewise representing it in a way such that the loss you're evaluating does not actually correspond to something that it can functionally learn or that exists in the real world, then you're going to run into some problems.
Also, you're allowed to share across customers. I mean, so can you use the images from Chipotle to build a model for Taco Bell, and do their guacamoles look alike?
I think their guacamoles probably look alike. I'm not sure with like all the lighting conditions. Most of our agreements with customers preclude sharing data between brands, but functionally kind of much of the work we do is kind of on the architectural and process kind of level of how we are actually representing things, how we actually get them labeled, how we get things validated, how we integrate with their point of sale systems. And so all of that is transferable. So while it would entail getting kind of different labeled data sets, a lot of the work is tied up in those other things. Yeah?
So, when new classes get added, after what time do you, I assume like the first time it gets added, you will try to, after what time do you say to retrain it or anything else?
So when they add things to the menu? Yeah, so a lot of fast food restaurants have limited time offers quite often. And so this is kind of an important thing to handle well. And we have kind of several methods of dealing with it. On one level, you know, we need to make sure we're working with them and we're appropriately integrated into their point of sales so that when we actually kind of see it come across the menu, we know that there is like something different that we should expect is being made, and that we're actually, you know, able to just on a basic level actually parse what it's saying there and kind of the already digital information, and then the kind of approach that we take to that broadly is one of continuity of if something just shows up, then it's hard to correct errors in terms of how it's prepared if we kind of haven't seen it before, but we can definitely avoid making kind of false positive interventions on it, and make sure that we are able to relatively quickly kind of bring into scope making corrections on the preparation of those new items.
I have two questions. The first one is relatively dumb, maybe. What is the name of the company? Is Agot?
Yeah.
How do you come up with the name?
So the answer is it stands for Agot Good Order Technology. It's a recursive acronym, but truthfully, it's a recursive backronym because we came up with the name before we came up with the acronym. Yeah, basically, we kind of looked through some short Greek names and weren't too picky, so we ended up towards the beginning of the alphabet.
And also, did you have to consider some like ethical issues? Maybe the employee doesn't want to get his or her face recorded.
Yeah, so basically, because our kind of camera views are top down, we don't actually see employees' faces very much, but also kind of more broadly, I think there is just a matter of like the expectation of privacy, and broadly there isn't kind of too much of a baseline expectation of privacy in a fast food restaurant, that you're around other people, they see what you're doing as well, and more broadly they have kind of cameras installed that are seeing things anyway. But it's extremely important to us that like we are something positive for the restaurant employees, and more broadly something positive for kind of all of the stakeholders in our value chain. So, you know, the line employee, the shift manager, the general manager, the area coach, the franchisees, the brand. And, you know, for instance, if the interventions aren't something that people kind of pay attention to and respond to by correcting the orders, then you know, the order accuracy product does not really achieve its end goal of getting those orders corrected. And so it's very important to us towards that end, and just for its own sake, that we are something kind of positive for the employees.
Good.
Yeah, along the lines of what you were talking about, where you can have ingredients with very visually similar looking features,
Yeah.
and sometimes the lighting conditions may change. Have you considered other sorts of input data apart from vision? Have you ever felt the need for that?
Yeah, so we have kind of at various points looked at other input sources. Some kitchens are kind of equipped with some IoT sensors, or kind of the control mechanisms for them are kind of digital already. We have looked at doing some things with audio. The kind of other data stream that we use is the point of sales data. So the answer is yes, but I think also one of the principles we operate with is functionally cameras can operate as relatively kind of universal sensors, that, you know, you could figure out if somebody, you know, put their hand over here by having some sort of IR barrier, or you could have a camera equipped with computer vision to just figure that out, and a whole litany of other things.
I wanted to ask a bit about your data set itself. Like, I assume your data set with the context of combination is private. I also see that some large places like Google sometimes release public data sets. It's like, how is like the trade-off of keeping a competitive advantage over your competitors versus like having like a pretty big working data set and come up with new models that you could possibly use in the future? Like, how is that like thought out?
Yeah, so we have actually worked with some teams for 11785 with some of our data in the past. The kind of trouble with kind of releasing public data right now, at least, is principally more one of the contracts that we have with brands and the ownership and kind of privacy of the data they want, rather than kind of any sort of competitive considerations. I think, you know, to the extent we're able to, you know, having kind of some public data and kind of stimulating some thought about kind of our problem space more broadly is something we're interested in.
I have two questions. The first one is, I think there is a trade-off between making the system working in real time and the upgrade of the system.
Yeah.
How did you deal with this problem? And the second one is, I want to know, I was wondering if the system works even if there are multiple workers.
Yeah, so I guess on the first question, the accuracy of the system versus the amount of compute required, there is certainly a trade-off there. I think it can be kind of less of a trade-off than it seems, for several reasons. One of them is, you know, if you're kind of thoughtful about which data you are processing and how, you can kind of extract a lot of efficiency from things. And secondly is, I'd say broadly, typically if you're running neural networks with kind of floating point 32 operations and doing full forward passes, you're probably using somewhere on the order of like 200 times more transistors than you need to actually do it. And to a significant extent, there are kind of good compute products that for inference take advantage of that and do kind of quantization and sparsity. And so that allows us to do a much higher number of operations with kind of less silicon and less cost for the compute. And sorry, what was the second question again?
I was wondering if there are multiple workers on the same screen.
Yeah, so more things I think I forgot to hit on the slide of difficulties is the kind of typical situation is there's multiple workers working together to make it, and there's also multiple overlapping orders being prepared, and we have to kind of deal with that not as an exceptional case, but as the standard case. And there's kind of an even greater extent to which it defies simplification, because it's not some sort of rigid segmentation where this person always adds the pickles and this person always adds the tomatoes. They work together, and if this person is kind of backed up with their work, the other person will come over and do that. So yes, it is something we deal with.
So the models that you've developed for different restaurants, the process is obviously different, so the data set obviously changes. But do you think the models that you've developed, the models that perform well, generally perform well over all tasks, or do you still have to make changes and like make decisions on the architecture front?
Yeah, so we have to make some changes and decisions on the architecture front, but broadly, the approach is kind of one representation, one model architecture across all brands, different kind of data sets and integrations on a per brand basis. Sometimes when we're working with a new brand, there will be kind of aspects of it that come up that are new, but the approach for that is broadly integrated into the single system and continue to just use one system across brands.
You mentioned that the scale of the data that you started with was like thousands of images. So was that much data sufficient, or did you choose the path of some kind of retraining the model with publicly available data so that you could tackle multiple different kinds of objects that could occur on the scene? Because there can be people moving or different kind of objects moving around her.
Yeah.
And you just are concerned about few objects.
Yeah, so I think as far as like pre-training, if you're using a architecture that like exists publicly, which for kind of the feature extraction, there isn't necessarily much reason not to, then there likewise isn't much reason not to use just like a pre-trained initialization. And even if there's something different with the architecture, it learns helpful features by learning the things in a public data set, even if you aren't predicting any of the things that are in the public data set. So yes, on the pre-training for the specific kind of use case we were starting out with, that kind of smaller amount of data was more or less sufficient. But I think a lot of that had to do with the relative simplicity of the problem in that restaurant, in Sushi Fuku. And so I guess kind of circling back to some of the difficulties there, typically in Sushi Fuku, items are prepared almost entirely by one person. There is not too much occlusion. You can see all of the ingredient containers. The items are moving relatively slowly. They're large items. They're usually well separated from others. The ingredients are reasonably well separated from others. You can see them grabbing the things from the bins. And there's probably a whole litany of other things that make that situation kind of easier. Yeah.
In the problem that you're solving, it's not really a computer vision problem at this point. It's a combination of a computer vision problem and a classic satisfiability CS optimal knapsack problem. So can you actually explain the different components of overall solution? How do you break it down and what do you guys actually do?
Yeah, so I think at this point, like a lot of what we're doing has to do with the kind of higher level way we are dealing with things, and I think there is like an overall principle, again with the inductive bias of if you are trying to predict what was made, your kind of default assumption should be that they made it correctly, because even though they get the orders wrong kind of far too much, most of the time they're still getting them right. I don't think I want to go kind of too much into the specifics, just because it's going to be posted on YouTube and everything. But a lot of it does have to do with the kind of higher level processing of this kind of signals information.
I'm guessing on a bad day, the system can still make mistakes. So I was just curious. I guess false positives are probably easy to track, but maybe true negatives are harder to track. So how do you guys like keep a track of the performance of the system?
Yeah, that's a good question. And so I guess, yeah, first off, we are fortunate in our problem space that, unlike some other applications of deep learning, nobody dies if we get something wrong. And so on occasion we can, and effectively, we waste a bit of the employee's time. We undermine their trust a bit in the interventions as far as their accuracy. But that is kind of an acceptable trade-off, and on the level of the brand, they make different trade-offs between how much they want the false positives versus the false negatives. We track kind of the false negatives several ways. So there are validation data sets that we get labeled for what was actually prepared. So we have people watch the video and mark that down, what was actually prepared, as opposed to what's in the KDS, and then we can see, of the orders that where what was actually prepared differs from what was ordered, what percentage are we intervening on, and then we can also look at for things like review and refund data, the impact we have, and get kind of a statistical sense of the impact we're having there.
I have a couple more questions, but I'll wait for the end.
All right. Yeah, I'll have some more time for questions at the end. And so, yeah, one problem I had kind of recently was to do with multi-set prediction. And, so we have orders and they have the various items in them. And, you can have two of the same of some items. So to set up kind of a toy problem, let's start out just keeping it nice and simple, and suppose that you have like a multi-set with a maximum size of 2, but orders vary in size and the sets vary in size. And again, just for a lot of simplicity, suppose our model is just f of x equals a. It's just outputting some constant set, but it's a learnable parameter of the model. So it doesn't pay any attention to the inputs, but it has kind of learnable outputs. And one thing you might do is you might read DTR and hear what they say about sets and how to approach it, and say should use the Hungarian algorithm, do linear sum assignment, find a bipartite matching between the two, da 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 da. So let's go ahead and do that. And so if you have kind of two instances of ground truth data, 1 and 2, and so you say you have a mini batch size of 1 and you're kind of doing gradient updates, and this is how your predictions start out, then you start out with instance 1, you assign it, you get a gradient that looks like that, you move it over, you go to 2, get a gradient that looks like that, you move it over, and you keep on going, and you end up stuck like that. So you each time are just alternating between this one being assigned to 1 and 2, and this one not getting assigned to anything, or getting assigned to kind of the empty prediction, or maybe it's moving over to some 0 somewhere. And this is obviously not what you want to happen. You want something like that to happen if you are caring about just there existing some predictions that are associated with the items. The particulars of that might depend on your loss function, but you can end up with a problem like that. And interestingly, recently had functionally this kind of problem where the learning procedure was set up in a way that did not appropriately kind of deal with these unassigned items, and had a broadly similar kind of failure mode. And I actually do not know if this is something that kind of happens more broadly, or how kind of on a practical level something like DETR actually deals with this and avoids these scenarios. But at least with our situation for this particular network, this sort of thing came up. And more broadly, there's got to be a better way. I think there's probably some dynamic program in doing the
this is kind of
optimal
analogous to the
assignments.
alignment problems we have in CTC, right?
Yeah, it's very analogous. And
so you have an assignment to be made while computing the loss.
Yeah, and so I had to discuss this a few weeks ago with Biksha, but I think there is probably some sort of dynamic program in there somewhere that can do this in another way, but not sure exactly what it would look like. And probably some degree of like a temperature aspect of it too, of how certain the assignment that was made would be to be made. But not sure exactly the structure of it, but it's interesting that this is a problem that came up, and coming up with this toy problem and working through it was the way I had gotten that resolved. So how about another one? So everybody wants like clean and perfect data, but it's pretty expensive, and what you really want is a model that works well. If you had bad data and your model works well, I don't think you would necessarily be too bummed out about it. Make sure you have at least good validation data to make sure it's actually working well. But if you can make do with bad data, then you may want to, because broadly, you can spend money on labelers, or you can spend money on engineers, and more broadly, you can have engineers on making sure the data is good and clean and analyzing it, or experimenting with different architectures, doing other work, or have labelers work on higher quality labels, or just more. And so, can you actually like learn with noisy labels, and like, is it a worthwhile thing to consider to make these sorts of trade-offs, or is it something that will just really screw you up if your data isn't clean? There's much ado about kind of clean data and data-centric AI and everything. So certainly the data matters, but what actually kind of matters more? Having kind of more data, putting your resources towards improving architecture and things, or making sure the data is kind of as clean as possible. To what extent does it matter? To what extent does it matter kind of in your particular use case? And so, to see about if it's kind of a worthwhile hypothesis, just set up kind of a simpler, a very simple kind of thing with MNIST of all things, and set up a data set that just randomizes some percentage of the labels. So, it's actually something that's known that some of these large data sets have a degree of label error, even if they've been kind of very heavily scrutinized of, I think, like, don't quote me on this, but maybe like 1 to 3% on ImageNet. And, networks seem to learn just fine on that, but, what about kind of significantly higher proportions, and what's like the relative impact of that versus kind of having a shorter data set? And, with the full trained data set, this particular network got 99.3% accuracy. Things get however many nines of accuracy with MNIST, but just the simple, stupid sort of thing. And with 20% of the labels randomized, it gets 99%. And with 50% of the labels randomized, it gets 98%. And with 80% of the labels randomized, it gets 95%. There are a lot of scenarios in which, getting 20% of your data correctly labeled is significantly easier than getting kind of 100% of your data correctly labeled, or kind of more broadly getting a data set of a size that would allow you to achieve the same accuracy. And then, it's 99% accuracy versus 93% for the data set with half the data. It's not conclusive since it's a toy problem, but it helps inform whether it's something worth looking into if you really want to spend the time and effort on, that incremental bit, or if you also want to look at different approaches to doing the labeling that might give you kind of lower accuracy labels, but feasibly could get you a lot more, could get you them a lot cheaper, a lot more easily, could kind of help you iterate quicker, all of these things. So, and you follow up with actually evaluating it on the real problem, but something like this is very informative, especially since it takes half an hour. And I was pretty surprised by that, and it raises some interesting questions. If you have a data set where half the labels are wrong, could you do better than with a data set where all the labels are correct but half the size? That conceptually, if you knew which half of the labels were wrong, then you have the same amount of supervised data and some additional unsupervised data. And you should be able to use that, but it's a bit tricky there. And also, could you use the information about the proportion of labels that are wrong to create a better training procedure? Like if you know you have some level of noise in your labels, could you set up a training procedure where you, for instance, tell the network, you can disregard the 30% of labels that you're having the most trouble on, because there's a decent chance that those are wrong anyhow. Do something like that. I'm sure somebody's kind of explored this further, but just kind of something interesting I thought I'd share. And yeah, open it up to Q&A, and also we are hiring, so you can check
Very nice. I wanted, so yeah, that's brilliant. And you guys start, CMU graduates just went out, had an idea, and I don't know where the idea began, and today here you are hiring more graduates, right? So what was the process from stepping out and saying, I'm going to start a company, to actually being where you are? Can you give us an idea of the path?
Yeah. So I had actually started out when I was still at CMU, or over kind of the summer there, and I guess as far as the initial inspiration, it was the very long lines at the Chipotle over on Forbes, and basically we started out not with kind of the order accuracy, but with looking at kind of automatic checkout, to basically in some place like a Chipotle where you order by talking to the person and telling them what to make, to just ring you up and not have a need for a cashier there, and ideally to get the orders kind of more accurately and everything as well. And the process was kind of, we worked on getting some sort of prototype. We kind of just walked in and got in touch with Ting, who is the owner of Sushi Fuku, and he's now the owner of Aratashi, because they kind of split that up, but anyhow, and asked, we want to work on this. Can we put cameras in your store? And he said, yeah, sure. And we did that. Got some data, and kind of just worked on packing on it to make something interesting that did what we wanted to do. And we did end up getting something that more or less was able to ring people up in Sushi Fuku, but we kind of didn't end up too actively pursuing that, because we ended up more actively pursuing things with kind of some large brands. But basically we had a kind of demonstration system with Sushi Fuku, and my business partner Evan worked on a lot of the kind of business development there, to get us in contact with the right people at these brands, to start working with them.
And so how long did the whole process take?
So it was about like a year and a half in when we kind of first started working with kind of our first major brand, and then we were able to kind of fundraise aggressively off of that, and kind of go from there.
And so now how large is the company?
We have about 35 employees.
Most in Pittsburgh.
About half in Pittsburgh. Any other questions?
I guess I was just curious, like, what is the average setup time for a new store?
Overnight. So, yeah, an installer comes in and installs the camera and compute and networking stuff overnight.
So isn't the system sensitive to the positioning of the cameras?
Yes and no. So I think it's a bit of a tricky thing, and broadly, you need to see the preparation of the food, but you want to minimize kind of the specific sensitivity of, minutia of where the camera is mounted or where it can be mounted. So we need to make sure we have visibility of the correct kitchen elements, and kind of consistent visibility of that between stores, but in kind of the design and approaches that we take, we try to minimize any of the like specific sensitivity to small changes in the camera position. So broadly, we want to see this part of the line, this part of the line, this area with the drinks, but not like it needs to be 4 centimeters from here or something.
Do you have any problems with like degradation over time with like cameras being like a hot or steamy or other environments like that?
Yes, we have to replace cameras on occasion. As far as like heat and steam, we try to the extent that we can, try to keep them away from that and have like cameras that have some protection for those sort of things. But there is sometimes like some cleaning that needs to be done. Yeah.
You mentioned the trade-off between like better data and better architectures. I guess in that perspective, like what has contributed more to the success of the company? Like what have you spent more time on?
Probably the latter.
Better architectures.
Yeah.
So what are the, I'm assuming not all customers are equally difficult, right? So to the extent you're allowed to tell us, what are the key challenges that you encountered when you got to a new customer? Have some examples of what kind of challenges you ended up with, technical, and how you dealt with it.
Yeah. So I think some of the major things are just how like vertically stacked and inclusive the kitchens are, having kind of small, fast-moving objects, having the ingredients and their visibility be kind of small and low, respectively. Yeah, I think those are kind of the principal things. There are kind of some pieces of minutia of just like how well defined is it based on their ops procedures, where exactly an order is supposed to be being prepared, or how exactly it's supposed to be prepared, and like there's a lot of information that is kind of implicit in the operations that is not necessarily like centrally documented in terms of like what is something they are allowed to do versus not to do, and kind of if it's kind of expected operations or if it can actually be handled as an exceptional case. And so, we'll talk extensively to their operations teams and try to get as good an understanding as we can, but that doesn't stop like us from finding something like 100 hours into the footage of just like what the heck happened. Yeah.
So you're, I guess, mostly using RGB data for this, or have you looked into using different kinds of cameras, say IR camera, plus different ingredients might also have like different temperatures and that might show up differently. And maybe like that information can also be helpful for, say, classification. Maybe you could use both, train different models on both and maybe ensemble the results and get better.
Yeah, so we have looked at IR, we've looked at a lot of things. So we have looked at depth and done some things with depth. We have looked at kind of hyperspectral things as well, and some IR things also. The nice thing about RGB cameras is they are very standardized and commoditized and relatively inexpensive, and are also doing the labeling then in the visible spectrum that is kind of more straightforward to do, that you don't necessarily need kind of some other source of ground truth or to give like labelers specialized training as well. Yeah, so we have considered kind of a variety of other options, but there are a lot of benefits to kind of keeping it relatively simple with RGB.
So, yeah, if things change, which would take a lot, let's say, remove some component to some other part of the new way, leave the ingredients, you have to go back and label it again. How does it affect the way
No. So I guess also more broadly, this connects to, you know, the way things are represented and approached. You know, it's a big consideration for us in doing that. What things we are not sensitive to and to what extent. So kind of some of the biggest things that we sought to be like non-sensitive to are like camera positions, precise positions of ingredients, and to the extent we can, you know, the sorts of variations between stores with like the lighting conditions or the precise angles that the cameras are at. But it's not something that it like comes naturally. Like the design work has to be put into to make sure that's the case.
Is there any plan to scale up? Maybe you can apply to some other main, like for example, like installing a camera in some household and for some like elder people who have some medical issues. It's basically a similar strategy.
So yes, there are like possibilities to scale to other industries. I think kind of the most applicable things for our technology would probably be like correctness of complicated procedures. And so it's not necessarily something that would be, I think, too applicable to household use. It is something that's potentially applicable to some manufacturing, medical, other
Retail,
sort of use.
generally, right?
What was that?
Generally retail.
Yeah, yeah. Yeah.
One last question, folks. We're out of time. Go
What
ahead.
does a day in your life look like? Is running a startup just as fun when you used to, as compared to when you used to work on like deep learning projects at same group?
That's a question I wanted to ask. Thank you.
Sometimes there's a lot of kind of other things involved, at least kind of with the stage we're at right now. Certainly kind of early on, I'd say the answer is yes, but kind of other responsibilities sort of start to come in a bit later. And so the work composition can change a bit. But yeah.
All right, thank you very much. Everybody, let's give our